event that we'll holding on Saturday. Okay, it's really very important for you to attend it. I mean, it gives you a clear view of what does it mean to work on math research in the summer. We held the summer research program for 7 weeks in the summer. There were 3 groups, and the groups did a great job, and the results will be shown on Saturday. So I really advise you, and I urge you to attend it. You're going to have a very good idea of how things are working in math. You're going to see it firsthand, and hopefully next summer you'll be participating in something like that. So on Saturday, October 22nd at 2 p.m. here. Okay, so try to make it. Okay, yeah. And I give the floor to Professor Ghaith.
This okay.
The pointer is working.
Okay, right. This one. Okay. Can you hear me? I think, yeah. All right. Thank you very much for continued interest and attending. So today I'll continue what we started yesterday, which basically one black box from yesterday was to actually how to numerically compute the Riemann zeta function on the critical line and in the critical strip in general. So my focus today will be on how to do this. It's a bit more technical than yesterday. Unfortunately, it's frozen. Okay. I'm not sure what the. Yeah, I just moved the kind of, there's a box down here I moved and just stopped. Okay. Yeah. Yeah. Right. It's the same. Okay. So, okay. So apologies, for some reason this box has to appear for the slides to move. I'm not sure what the connection is. It's probably harder than the Riemann hypothesis to figure out. So let's just leave it like this. Yeah, so I'm going to start with a review of some of the things that we mentioned yesterday. So we have this kind of symmetry for zeta by the reflection principle. So we can restrict our attention to the upper half plane. So when the imaginary part of S, so S is usually sigma plus IT, T would be the imaginary part. Because of this symmetry, we can restrict to T non-negative, right? And we also have the functional equation where C of S is defined this way. And because of the symmetry provided by the functional equation, we can further restrict to sigma. So sigma is the real part of S that is greater than or equal to 1/2, right? So overall, when computing zeta in the critical strip, we can just consider sigma between 1/2 and 1 and T non-negative, right? Okay. So I need to kind of a little informally say what it means to compute zeta, right? So this means to numerically compute zeta function is to get a numerical approximation bounded by an error, say, of this form. So the form is the size of S plus 3 to the minus lambda, where lambda is some positive constant. For example, lambda is equal to 2. So in a sense, this is saying that at larger heights, right, you want more accuracy. I mean, there is a good reason to require higher accuracy at larger height, because if you look at one of the functions that was defined yesterday, the zeros counting function, n of t, this counts the number of rows, the number of non-trivial zeros of zeta with height between 0 and t. If you look at the behavior of this function by the argument principle is given by this form, and theta t is asymptotic to t over 2 log of t over 2 pi, right? So because of this asymptotic or this size of theta t, we know that n of t behaves this way. So up to high t, you have more than t zeros, right? So you have in a distance of t, you have more than t zeros. So the spacing between the zeros is getting smaller and smaller. They're getting denser and denser. So at high t, you can calculate from this formula that the density is about is asymptotic to 1 over 2 pi log of t over 2 pi. Right, and from this you can get the average spacing just by taking 1 over this quantity. So if you look at high t, then the average spacing would be 2 pi over log of t. So the average spacing is decaying with t, like logarithmically, not very fast, but logarithmically. The zeros are getting denser. And you can visualize this. Here is the blue line here. This is a plot of n of t when t is between, I think, 10 and 40, so right at the beginning. And the kind of yellow or orange line is a plot of s of t, which is that remainder term that has jumps by 1 or by more at the zeros of zeta. And you can compare the shape of s of t at the beginning, right here, with the shape of it when you go higher. So here's what s of t looks like when you look around 1,355. And you can see that s of t is moving much faster because the zeros are getting denser. The spacing between them is getting smaller. Right. Okay, any questions about this? Right, so because the spacing is getting denser, maybe you need more accuracy to separate them by sign changes. Right. Let me also mention computations with zeta on the real line, which is a different situation, but very interesting, right? And there's another reason to mention this is because this formula will be important later. So on the real line, there are special points, namely non-positive integers and even positive integers, where you can get not only a numerical approximation, but an exact value for zeta, at least in terms of fundamental constants like pi, right? One way to do it is to use this formula here, which is the starting point for one of the many proofs of the analytic continuation of the zeta function. This formula is from complex analysis, and you have a contour integral here. The contour C looks like it's like around the origin and looks like the shape of a keyhole. We're not going to really be referring to it much later, but if you want the details, they are in the notes I sent in some of the emails. Right, so if you look at the inside here and you use the following, right? You use the generating function for the Bernoulli numbers. The Bernoulli numbers are important numbers that come up in many different contexts, and they're given by this generating function. So if you do a Taylor expansion of this function around z is equal to 0, you get these coefficients, and the coefficients are equal to the Bernoulli numbers, starting with z squared and then z to the 4th, and so on. right? So if you take this formula for the generating function and plug it back into the integral representation here, so you multiply and divide by z, which you're allowed to do because your contour never passes 0, it's around 0, right? Then you use Cauchy's theorem from complex analysis to evaluate the residues. You get the value of zeta at 0 is -1/2. And then you get the value of zeta at the negative integers, negative even integers at 0. So these values are what we call the trivial zeros of zeta, right? On the real line, the only real zeros of zeta. So we have a proof of this by using the Bernoulli generating function together with that integral representation. Another proof, at least. Right? And you can evaluate also by this method the values of zeta at the at 1 minus 2m, so at the odd negative integers and at the even positive integers, zeta of 2m. And the values are given by the Bernoulli numbers, or maybe you need to consider pi, powers of pi here. So we have exact evaluations at these special points, but other than this, we don't really have that exact evaluation. Okay, well, to compute zeta in the critical strip, what is, like, to simplify things a little bit, here's the main thing, or here's the main sum that we need to numerically approximate. It looks like a finite version of the Dirichlet series that defines zeta originally, right? So it's like k to the minus s, so s is equal to sigma plus it. So if you take the sum between k0 and k1, then, and there's a typo here, I mean as k1 goes to infinity, basically if you look at the sum from 1 up to n and take n to infinity, you get the usual Dirichlet series for zeta, right? Provided that sigma is greater than 1, right? But this Dirichlet series diverges when you're inside the critical strip. So you can't use it, directly. But there are methods where you can actually approximate zeta still by a finite sum of this form. And this can be done using methods like Euler-Maclaurin and Poisson summation, which I will discuss today. And these are the main methods I'll discuss for computing zeta today. The Poisson summation will not come up, at least maybe directly, but it will come up in the form of the Riemann-Siegel formula. Right? So, well, at the end of the day, you can reduce computing zeta on the critical line or in the critical strip to computing sums of this form, where the length of the sum, which is about k1, is going to be bounded by something like t, or t to the 1/2, or t to the 1/3, or the fastest asymptotically is t to the 4/13 length, right? These ones, 1/3 and 4/13, they're very complicated. I'm not going to talk about them, but I'm going to talk about the method which gives you a sum of this form, which has length t, and a method that gives you a sum with length square root of t. Okay. Are there any questions? Okay. Oh, okay, so let's start with the Euler-Maclaurin formula. This is kind of a beautiful application of calculus, basically. And in fact, this formula was the one used up to about 1930 to do computations with zeta. Before this formula was used, people actually used the Hadamard product to try to approximate the zeros. But this was you could use it for low heights, but once you get past a small threshold, it becomes very bad or very inefficient. So around, I think, 1903, the first paper came by Gram from the Gram-Schmidt process. If you're learning about this now, he's the same. He was interested in zeta. Gram, he was the one who did the Hadamard product method, actually. but then came back in 1903 and they discovered that he could use something called Euler-Maclaurin summation, which works much more beautifully. Okay, so what is this? You look at a continuous function like over an interval a to b, and you assume that this function is differentiable. You define these things in the usual way. So this is the floor of x, and this one here is the fractional part of x. Then you have this under these kind of assumptions, and you assume a and b are integers. There's a form of this where a and b are not assumed to be integers, but we don't need it. Right? So if you assume a and b are integers, you have this kind of approximation. You have that the sum between a and b of g of n is given by an integral plus some boundary term. These are boundary terms because these are the values of g right at the beginning and the end of the sum, plus some funny looking integral, right, which we're going to think about as a remainder term or a correction term. Right, and the idea is that if you look at this integral, which looks the hardest to compute, in general, you know, this is if g has an antiderivative, or if you use a numerical integration, this is computable pretty easily. And these are just two terms. So really the most mysterious part is this integral. If the derivative of g is small in size over the integration interval from a to b, then you can bound this by something small, right? And this is the idea of Euler-Maclaurin. If your derivative is small enough, then you can approximate this sum by an integral plus a boundary term. And this whole formula is proved using integration by parts from calculus. Okay, so the idea of the Euler-Maclaurin method is just to apply integration by parts repeatedly over and over. And when you do this, you get not just one, but not just a boundary term and a correction term, you get a whole sum of correction terms, which are given in terms of the Bernoulli polynomials, Bernoulli numbers that I mentioned before, and in terms of the derivatives of your function g, and assuming that g is actually differentiable over that interval from a to b. And then you still have this remainder term, which looks hard to compute, right? And in that remainder term, you have something called the Bernoulli polynomials. And here are the first few Bernoulli polynomials. The basic observation is that the integrand here consists of the kth derivative of g to get multiplied by the Bernoulli polynomial. And then on the outside, you have a k factorial. And you can bound the Bernoulli polynomial over k factorial by 2 zeta k over 2 pi to the k. Okay, so there are several things. We're just taking the max here between 0 and 1. And this is really the only use that are relevant here because you have b sub k of the fractional part of u. So the fractional part is always between 0 and 1. So to kind of bound the size of this, you can just consider u between 0 and 1. The second thing is zeta of k. As k goes to infinity, this zeta of k goes to 1. So basically, you're saying that this quantity is bounded by something like 1 over 2 pi to the k. So it decays exponentially with k. And this is how you can achieve good error estimates using the Euler-Maclaurin formula. And assuming that your kth derivative is not too large compared to this quantity, basically compared to 1 over 2 pi to the k. It's just like an application of integration by parts. Okay. Yes. Yeah, so we're summing over integers and between a and b. Yeah, so greater than a and less than or equal to b. Right. Are there any other questions? I don't know why I keep on going the other way. Right. Okay, so you can. Sorry. You can apply this to the zeta function. But the thing is, when you apply it, you want to apply it to the tail of the Dirichlet series that defines the zeta function. When sigma is greater than 1 by convergence, you have zeta of s is equal to this sum, an initial sum plus a tail sum. And then you can apply Euler Maclaurin to the tail sum. And once you do this, so your g of x would be x to the minus s. Right? When you apply Euler Maclaurin, the function that comes here, g of x, when you apply it to zeta, it will be x to the minus s. And then you go through the whole process, you get this expression. But then by these estimates we talked about for the Bernoulli polynomials, you can prove that the remainder term, which involved them, is actually analytic for sigma greater than minus k plus 1. Here I took k correction terms. And so this formula, even though we started assuming sigma is greater than 1, actually provides a continuation of zeta to this half plane for sigma greater than minus k plus 1. So you can apply it on the critical line, for example. Okay, and you go through the estimates on the previous slide, you can prove that the remainder term here, assuming k is equal to 2m, so it's even, satisfies this complicated expression. Okay, there are several things maybe to point out. Why take k to be even? This is because the Bernoulli numbers, when k is odd and greater than 1, are 0. Right, so you may as well go to the next step. So you can assume, without loss of generality, that k is even. The second thing is, what is the size of this remainder term? The main thing to observe, this is this product here, right? So in this product here, you have basically the size of s divided by 2 pi n. And you're taking a product up to 2m. So if you want this product to be small, right, you can do it by making sure that each term is small. And if you think of s as approximately equal to the height t, then to make this term small, you will want n to be at least t in size. The stuff on the outside, this term tends to 1 as little m goes to infinity, so less important. This one is just like just a single power of t, which you can essentially remove by the exponential decay coming from this product, provided that big N is large enough, bigger than t. Make sense? Right, so, okay. And one way you can, think about in terms of the remainder term, it's about the same size as the last correction term in the Euler Maclaurin formula. So here's the Euler Maclaurin formula applied to zeta. Here are the correction terms. The term when little k is equal to big K will be about the same size as that remainder. Right? And as I mentioned, you need n to be at least the size of t to get any type of accuracy, so that the product that occurs there actually decays exponentially as you take more correction terms. Okay, but this is very technical. Is there like an intuitive reason why the Euler Maclaurin would require you to take a main sum, like a Dirichlet polynomial of length at least t to get any type of accuracy? The reason is really simple. If you look at the sum we have and you kind of write n to the s as e to the minus s log of n. So you exponentiate, take logarithm and exponentiate. Then the main thing what you have is a phase function, like, and your phase function looks like t log n. Okay, so this is the phase function that occurs in the nth term. And if you look at the derivative of this phase function, it's t over n. So the observation is that when n is greater about the size of t, the phase function has a small derivative. So it's changing very little. right? So there's very little cancellation that happens in the sum. And for this reason, when there's little cancellation, the sum, because it's kind of moving in a very regular way, can be approximated by an integral. It's essentially a Riemann sum that approximates the integral. Yes. Oh, this one? Yeah, it's discrete of n, but you can replace the n here by an x if you want. So I'm just looking at this as I'm extending the definition of this to say positive n. Maybe I should have written x instead of n for this part, but I just wanted them to be more comparable. Okay. So I mean, we're really summing this phase function when n is just an integer, but the function makes sense even when n is just a positive, any positive number. Any other questions? Right, so this is why the Euler-Maclaurin works. It's basically once you get past length t, then the remainder of your sum is moving in a very regular way. There's very little cancellation and it's basically approximated by an integral. Right, so the advantages of this method is that you can estimate the remainder easily. And by taking n larger than about t over 2 pi, for example, let's take n to be 10t, then you can get very good accuracy, exponential decay in the remainder. And this is the main reason why this formula is still used even today. Right? It's because it gives you a very accurate way. If you need to very accurately get a value of the zeta function, you can do this with the Euler-Maclaurin summation, at least when t is small in size. But the main disadvantage is that the formula is inefficient when t is large, right? It has a very long main sum. And so, you know, it becomes like really hard to work with it. Like imagine you want to compute when t is about 10 to the 10, then you need to sum about 10 to the 10 terms, which takes a long time. Right, so now I come to the next method, which is the Riemann-Siegel formula. So in this method, this came starting around 1930s. So Siegel discovered this formula in Notes by Riemann. And I believe Titchmarsh, who wrote like a basic or standard reference on the zeta function, was the first one to apply that formula. In the meantime, Turing came up with his own formula, which resembles Riemann-Siegel, but was more complicated. And he tried to implement his formula. There were no digital computers at that time. He tried to build a mechanical machine to implement his formula to compute zeta, but stopped, you know, Second World War came up. So came back to the same problem, Alan Turing in the 1950s, beginning of that. And at that time, he realized there was something called Riemann-Siegel formula that he could use, so he just used that. So the Riemann-Siegel formula has an interesting history, and it's been the starting point, at least, for computations with zeta for at least the last 80 years. So even in the methods that say instead of do a mean sum of length t to the 1/3 or t to the 4/13, they start with the Riemann-Siegel formula, and what they're doing is that they're re-expressing the mean sum in that formula using a shorter length, right? So that's usually the starting point. Okay, and so it has a shorter mean sum, about square root of t rather than t, but the accuracy that it can provide is less than Euler-Maclaurin. But still, you know, that accuracy is enough to separate zeros even at very large heights, going as high up as 10 to the 36. And even more should be fine. Right, and what the one way to write it is for zeta on the critical line, but instead of computing zeta, you compute a real version of zeta called z of t, which is defined this way: e to the I theta t times zeta 1/2 plus it. So the theta t here is the same theta t that came up in the zeros counting function, right? Remember the main term, the zeros counting function was 1/pi theta t. That's the same theta t. And from the previous lecture, there is a very simple and accurate way to evaluate theta t for any t. So there's no issue with it. And by defining things this way, you can show that z of t is a smooth function, and it's basically proportional to c of 1/2 plus it, which we already know is a real function. So z of t is a real version of zeta on the critical line. It has the same magnitude as zeta, and therefore it detects the non-trivial zeros, either by sign changes or by vanishing. The problem with the C function is that there's a gamma factor. So when you go up very high up at the critical line, the gamma factor has exponential decay, right? So essentially this Z of t divides out the gamma exponential decay. Okay, so let me state the Riemann-Siegel formula. You have, it's a very precise formula, like there is less choice over the parameters. For a given t, you define tau to be t over 2 pi, and then k1 will be the length of the main sum in the Riemann-Siegel formula. It's equal to the floor, basically the floor of the square root of t over 2 pi. That's why the main sum has this length. And then this parameter z will come up in the correction terms. It's some number between -1 and 1, right? It's equal to the fractional part of square root of tau, right? Because it's square root of tau minus k1. So that's the fractional part of square root of tau. And then after rescaling and shifting, you get a number between -1 and 1. Okay, and then for any non-negative number m, you have z of t is given by a main sum of length k1. In the main sum, instead of e to the it log k, we have cosine. The reason the cosine comes up is because of the symmetry. You have a number and its conjugates coming up, and so when you put them together, you get just the real part, which is the cosine. Right, and the minus theta t in the inside, this comes from here. You know, you can move this inside the exponential and then take the real part, so you get this term. And then you have correction terms. And this was, these correction terms, they're very hard to derive. The first one, when corresponding to j is equal to 0, is given by this function. And then you can take more of these. And then you have a remainder term r sub m of t. Okay, so there are formulas for the higher correction terms. They are given in terms of derivatives of phi sub 0. Okay. Right, so, but they're complicated expressions. The second thing is, even if you just look at phi sub 0, you need to be careful when you compute it, because like we mentioned z is a number between -1 and 1. Well, what if z is 1/2? Well, what do you have in the denominator? You have like a 0 of the cosine. The thing is, this is a removable singularity because there's also a 0 of the numerator. They cancel. But numerically, if you're evaluating that function very close to 1/2, you need to use some sort of a Taylor expansion so that you get, like an accurate approximation. You're not dividing like a very small number by another very small number, which could, give you like really random stuff. So there's this issue. At the end of the day, this is an entire function in Z, but it's not periodic in Z. And we need its values only for Z between -1 and 1. Right? Okay. And for the remainder term, gap key in I forget, like 1960s or something, he wrote his thesis on bounding explicitly R sub m of t. Like to get bounds, like where you get actual constants, you can tell that R sub m of t is less than a given number. Not that it's approximately less than this or that. You need an actual number, because without such an actual number, you cannot tell how accurate your computations are. So he wrote something like 100 pages or more. It's like a big thesis, very incredible achievement that he did this, given how hard it is and technical to derive the Riemann-Siegel formula. And he came up with explicit estimates for R sub m of t or tau and t are related directly for the first 11 correction terms. So here are examples. He assumed t is at least 200, so his estimates assume that t is large enough. When t is less than 200, that's a finite range. You can use Euler-Maclaurin. That's not an issue. So when t is greater than 200, he proved that the first 10, 11 correction terms satisfy certain bounds. So here are the first three. And going up to R sub 10, you have this bound here. Okay. And this is excellent because it actually allows you to do computations and to tell how accurate your computations are. In practice, even the estimate for R sub 0 of t is enough to resolve zeros, because the size is t to the minus 3/4. So if you imagine yourself, like imagine t is like 10 to the 20, right? So you have like 10 to the minus 15, like error, which is very good. Typically, the plus minus 10 to the minus 8 is like the, enough to resolve zeros in all computations that have been done so far. Right, so even R sub 0 by itself is good enough, but he derived all the way up to R sub 10. Before him, actually, Titchmarsh, to be fair, derived an explicit bound for R sub 0. That's how he was able to do the first computations using the Riemann-Siegel formula. But the gap key bound went much further for many more correction terms and obtained a better bound, like better constant here, like 0.127, and a better assumption on the lower bound for t. So it is applicable for as soon as t is greater than or equal to 200. Essentially optimal, right? Meaning that if you think of this, when we talked about the Euler-Maclaurin summation, right? We had a bunch of correction terms, and we had a rule of thumb that the remainder is about the same size as the last correction term, right? So this is a general behavior when you have an asymptotic series of correction terms. And the correction terms in Riemann-Siegel are an asymptotic series of correction terms. So if you look at the last correction term you're taking, the bound for R sub 0 of t matches the size of that last correction term. So you cannot hope in general for something better than this. Maybe you can hope for a better constant, but not for a better exponent in t. Actually, I think people proved that I'm not sure if people proved that the series of correction terms in Riemann-Siegel is actually divergent or not. Yeah, so I'm not, but it's for sure, almost surely divergent, just from the form of it. Okay, so let me try to motivate the Riemann-Siegel formula. I cannot give the proof, it's very technical, but the starting point is this integral representation that I talked about at the beginning, where we plugged in the generating function for Bernoulli numbers to evaluate zeta at some integer values, right? And to kind of try to motivate the formula, let's look at one of the terms in the main sum, which is n to the minus s. So you can write this way, like n to the minus sigma. Sigma is the real part. And then exponentiate, take the logarithm. You have n to the minus it becomes e to the minus it log n, right? So this just this way of writing this term basically is to isolate the phase function, which is t or minus t log n. And so you can see the phase function here. So when n changes, say, to n plus 1, then the term n to the minus s will be close to the term n plus 1 to the minus s. And this is because the part with n to the minus sigma will be changing very, very slowly. So almost no change or very little change. The part that can be problematic is the phase function. But when n is large, greater than t, then the phase function at n plus 1 is about the same as the phase function at n because of this expansion. The difference between them is about t over n. Right? Okay, so once you get past that point t, your terms are like behaving in a very predictable way, unlike what happens when n is below t, where the phases could be jumping anywhere in the unit circle. You don't know, that can be random. So there isn't an obvious way to kind of find a pattern in them, right? So, okay, so the Euler-Maclaurin takes advantage of this. When n is greater than t, it's approximating the Dirichlet polynomial by an integral. This polynomial becomes like almost like a Riemann sum, right? But when n is less than or equal to t, we don't have this kind of advantage. So it looks like our terms are, unrelated to each other. So like what kind of thing can we do? Well, even though the phases are changing quickly when n is less than t, they are still changing in a smooth way because your phase function is a smooth function. So you can apply the Poisson summation. And the Poisson summation allows you to relate the values of summing the function to the values of summing essentially a Fourier transform of the function. So if you apply this to the Dirichlet polynomial for zeta, what you find is that the sum of the Dirichlet polynomial up to square root of t is related in a very simple way to the sum between square root of t and t. So all you need to do is compute the sum up to square root of t, and then you can recover the rest by this simple relation. And beyond t, you can just, use the Riemann correction terms or use the Euler-Maclaurin correction terms. Right? So even though the individual terms over n behave randomly, they're not related to each other, like comparing n, the term for n with the term for n plus 1. If you look at the whole sum, it's related to another whole sum. Right? And this kind of symmetry provided by the Poisson summation is how you can go from a main sum of length t down to a main sum of length about square root of t. It's just Poisson summation. Okay, and Riemann's innovation was, okay, what do I do with the rest? Things going beyond square root of t, he discovered basically an exact evaluation for the remaining stuff, which is given by this function phi sub 0 of z and plus derivative of that function. And it's amazing that such an evaluation exists, right? There's no reason to think that you can do this beforehand. Okay, are there any questions? I'm sorry, this is maybe a bit more technical than before, but yeah. Okay, right, so with the formulas that are on these slides, there's enough to detect the first 10 zero ordinates of zeta using sign changes of z of t. So you can use Euler-Maclaurin summation, because to apply Riemann-Siegel, you could apply it and see what happens, but the explicit estimates you have for the remainder of Riemann-Siegel assume t is at least 200, right? That's the gap k work. But here we're looking at a t which is less than 200. So you can use maybe Euler Maclaurin and think about how many correction terms you want to do. And then once you can to actually locate sign changes, you can just use a simple bisection method, right? Kind of zooming in, successively zooming in on the interval where the sign change happens. Right. Okay, so there are now several improvements, not to go below square root of t in terms of the length of the main sum, but to save like a logarithmic factor. So like instead of square root of t length sum, you have square root of t over log t, let's say, or over log t. So you can do this using Euler product. So here's the Dirichlet polynomial we're looking at. The observation is that you don't need to compute all the terms in this polynomial. You can say pick a number p, which is a primorial, a product of the first h primes, and then just really compute or consider the terms here where k is relatively prime to p. So like say p is equal to 2, right? Then you'd be looking at k which are odd, right? And the reason this is useful is because then you, for each k which is relatively prime to p, so in the example when you're just taking 1 prime 2, this would be for each odd k, the terms you're summing, you would be summing these terms over k relatively prime to p. And it looks like we haven't achieved anything because we have this other sum, this whole new thing on the inside. But the reason this is useful is that this new sum here on the inside is going to be the same for many k's. This sum on the inside, which is basically it can be one of a small number of possibilities. So you can pre-compute these possibilities and then just sum over the k's that are relatively prime to p. So if I take 1 prime, then I would need to sum up about half as many terms instead of the original length. So I speed up the whole thing by a factor of 2, just by this. And if I take more primes, I can speed up more and more. Asymptotically, you'd be speeding up things by like a log t factor. Right, so you can do an idea like this. Okay, the other thing is like the rigor of the computation. So the rigor of the computation depends on really the purpose you want to do the computation for, in my opinion. You know, if you want to do statistics of the zeros of zeta or the zeros of an L function, then you can use heuristic arguments to think about the sizes of the round of errors that come up in your implementation. But if you want to do something like proving the Riemann hypothesis over a given interval, then maybe you need to do something like a formal analysis of the round of errors, or use like an automated thing like interval arithmetic. Right? But okay, let's consider both situations. On the kind of practical side, usually like, you know, there's human error, but if you get the same results using different machines, different algorithms, like changing the parameters in your algorithm and still get the same results, and using independent implementations, that's usually very, very good evidence that you've done things correctly. And that's actually how I do actual math. Not only like numerical computation, right? So like you wanna like eliminate do the most you can by these methods. So if you get this consistency, then you usually are confident that the results are numerically correct. I mean, if you do a mistake, make a mistake somewhere, there's no like bell that's gonna ring and say you made a mistake here. Like if there's a subtle mistake, somehow you have to find it. And this is a good way to try to look for mistakes, right? But still, even though this is a good check, it's not a rigorous proof. This is not like what we call a rigorous mathematical proof of correctness, right? Okay, so here's an example. Suppose you want to compute zeta at like s is equal to 1/2 plus 10 to the 2mi. So t here would be 10 to the 2m. And suppose k0 is 1 and k1 is about square root of this. So this would be like what you'd get if you're using Riemann-Siegel formula, right? Because with Riemann-Siegel at high t, you get a mean sum of length about square root of t, right? So we want to compute now this thing up to k1. Right, the issue comes up when you compute the phases of the individual terms. So the phase for the kth term would be it log k, and t is a large number. So when I reduce this to pi, but after reducing to pi, you lose a lot of accuracy because you have reserved many of your digits in the finite precision that you have to actually capture the size of t, which disappears with modding. Right, so this is an issue. We lose a lot of accuracy because of roundoff errors when we do modulo 2 pi. Right, so if you do this, like suppose you're using d digits to do the arithmetic on a computer, then the error you get will be, you know, the contribution of the kth term would be like epsilon sub k over square root of k. And the epsilon sub k here will be bounded in size by something like 10 to the 2m minus d log k. So the important part is this one, 10 to the 2m minus d. You lose 2m digits of precision because that's how much it took to express the size of t, which is of size 10 to the 2m. So if you just use a triangle inequalities and bound the variance of this number, of this error, then all we know is that it's bounded by, you know, the machine precision 10 to the minus d, basically, no, so sorry, 10 to the 2m minus d multiplied by, you know, if you sum 1 over square root of k here and approximate the sum by an integral, then this would be about 10 to the m over 2. Right? So this would be an issue, like, for example, even using double precision arithmetic, standard arithmetic on a computer, which would give you about 15 digits. So D would be 15 digits. Then you want to go just like a modest height, 10 to the 11. Then using that estimate on the previous slide, all we can say is that the error is bounded by 1.55. Right? But like at height 10 to the 11, the average spacing between zeros is like from that formula at the beginning is like 0.2674. So the error is larger than the average spacing. So this is not useful for separating the zeros. Right, so the solution maybe the obvious one is, well, use more digits. There's an issue when you use more digits is that you lose access to the fast double precision arithmetic and you have to use multi-precision arithmetic. This could be a loss of a factor of 100, depending on which operations you use. So you know, if you gained like a factor of 2 using the Euler product on a previous slide, you lose a factor of 100 when you move on to multi-precision. So this would be increasing the digits would be an immediate solution, but very expensive. If time-wise, right? On the other hand, you can think about the epsilon sub k's that come from reducing modulo 2 pi, that they would be really behaving like random independent variables. Random variables. So when you have independence of random variables, you have that the variance of the sum is equal to the sum of the variances. So then typically, if you calculate the variance under this assumption, instead of epsilon times 10 to the m over 2, you get epsilon times log of 10 to the m, much smaller quantity. And so the error, the round-off error you'd get would be much smaller, typically. This is like called, you know, so basically you're saying you expect square root cancellation in the round-off errors. It's less than 1. Oh. This,
Will it be less than percent?
this one here. The space, yeah, oh, I actually didn't calculate the spacing at the, but I'm pretty sure that it will be less, yeah. Because the log of 10 to the m, when m is like, like 2m is 11, so this logarithm would be like at most 100, and epsilon is already of size like 10 to the minus 15 plus some like small integer, so this will be far less than a quarter, which is the average spacing at that height. Okay, so you have this kind of issue, the round of errors. Like, do you do a formal error analysis, or do you use heuristic arguments? It's like a substantial project, or do you use interval arithmetic? It's a substantial project, either way. But you can actually cut off a lot on the loss in the time if you do simple tricks like this. So instead of computing the phase function or the reduction of the phase function modulo 2 pi very accurately for each k, you and for a given t, for many t's, if you're computing zeta at many t's, you do the computation accurately for a single big T, and then for nearby t's you use an expansion like this one here. And this expansion can be done using double precision arithmetic. So the expensive part of multi-precision would be just to do this reduction here, modulo 2 pi. And the rest can be done much more quickly. Okay, so I think that's it. Thank you.
Any questions? Any questions? Okay. Okay, just any questions for our attendees online? Can you please write it in the chat box if you have any questions?
I'm sure how to. I don't know if there's no chat that comes from.
Okay, thank you very much. So see you tomorrow, guys, for the Wednesday. Okay, have a good day. Good night.